Welcome up Karthik and Garimella. Did I say that? Woo! I'm good. Thank you all. So we're going to, shift a little bit from some systems isolation mechanisms here to some private inference and magic stuff that I'm not really great at. So audience members, I will rely on you to ask important questions here. No. We're here about characterizing and optimizing end-to-end systems for private inference. Go ahead.
All right. Thank you so much. Let me just see. All right, thank you so much for the introduction, and thank you all for coming. I'm very excited to talk about our paper with, sorry. Let's try that again. All right, hopefully this works. I'm very excited to talk about our paper with my wonderful colleagues, in which we conduct the first end-to-end characterization of private inference protocols. Let me just see if I can. I'll just try to balance it here. Okay, yeah, so, okay. All right, thank you. Yeah, so in this work, we perform the first end-to-end characterization of private inference protocols, and we identify a fundamental bottleneck in prior work in which they assume that the pre-processing costs of these protocols can be ignored. And in our work, we show that this is actually not the case. And so we propose optimizations to mitigate these pre-processing costs, and we observe a speed up in latency as well as an increase in maximal sustainable throughput. And finally, we open source and release our tool called Kryptonite, which allows researchers to figure out the system level effects of their own private inference protocols. So just to set the stage with private inference, we have two parties, a client and a server, where the client has some data and the server has trained and deployed a neural network that the client would like to query. And just to give you a concrete example, suppose the server has trained their neural network on proprietary hospital data, and the client maybe has some sensitive personal medical data, but they still want to leverage this model to get some sort of diagnosis. So in order to securely perform this inference, the idea in private inference is to perform this computation directly on encrypted data, and in order to preserve the privacy of both parties. And so in order to perform encrypted neural network inference, we have to use several cryptographic primitives. And the two workhorses of private inference are homomorphic encryption and garbled circuits. So we'll spend just a bit of time going into both of those. So with homomorphic encryption, we can think of this as secure outsourced computation that's well suited for linear layer evaluation or linear transformations. And this can happen directly on encrypted inputs. So in this case, the client has some data, they encrypt it under HE, the server performs this linear transformation directly on encrypted data to get an encrypted output. They can send this back to the client, who can then decrypt it locally. And in contrast with garbled circuits are a multi-party computation paradigm, and the idea is that this is well suited for Boolean functions. So here the two parties have agreed upon some Boolean function to compute, and the way this works is one of the parties, in this case, will garble or encrypt this Boolean circuit. They'll send these garbled circuits to the client, who can store them. And then once the inputs are available to the garbled circuit, the client can evaluate this garbled circuit to produce an encrypted output that can be sent back to the server or the garbler, who can decrypt this locally. So let's see how we make use of these crypto primitives in private inference. So here we have our neural network, And we assume we have two types of layers, convolution fully connected, which are linear layers, and the ReLU activation function. And so since the convolution fully connected are linear transformations, this is where we use homomorphic encryption to securely evaluate these layers. And then ReLU is well expressed as a conditional, so we use garbled circuits, and it's common in these protocols to see the server performing the garbling of ReLU, sending that to the client, and you see the client storing these ReLUs and actually evaluating them. And in this setup, the big costs come from the homomorphic evaluation of the linear layers, as well as the garbled circuit transmission and storage. So let's quantify those costs. So here in this example, we'll be looking at ResNet 18 on TinyImageNet, which is a classic image classification data set of size 64 by 64. And let's just look at some of the costs. So with client-side storage, the client has to store 41 gigabytes of garbled ReLUs. And the catch with garbled circuits is you can only use them once. And so this is actually a per inference cost of 41 gigabytes. For compute, we find that the homomorphic evaluation of the linear layers dominates the compute stack, and for this network it takes 18 minutes for the server to perform the linear layer evaluation under HE. And finally, with communication, even at a high bandwidth of 5G wireless at 1 gigabit per second, it still takes 11 minutes to transmit these garbled circuits from the server to the client. And prior work has shown latencies on the order of seconds to a few minutes. So how are they dealing with these large system costs that we're seeing right here? And so the trick in private inference is to split our protocol into two phases. So the first phase is a pre-processing phase that is input independent and can be done a priori. And then the second phase is an online phase, which happens once the client's data is ready and they want to actually perform an inference. And what you'll see is we'll move these heavy crypto primitives to this pre-processing input independent phase and use our lighter weight crypto in the online phase. And just as a side note, since we moved the linear layer evaluation to the offline phase, we have to bring in one more crypto primitive called secret sharing, but it has negligible system level and latency costs. And so pulling in those numbers from the previous slide, we'll see that in the pre-processing phase, we generate all this pre-compute, and we can use that pre-compute in the online phase. We can consume it to have a low online phase latency, in this case of just 4 minutes. And so this is where the big assumption of prior work comes in, which is they assume that these pre-processing costs can actually be ignored. And in our work, we show that this is not the case. And really the problem comes out when we move from thinking about just performing a single inference to a client requesting multiple inferences over a period of time. And so here, again, it's the same network and data set. We've set the client-side storage to 128 gigabytes, and on the y-axis is the client's observed latency, and on the x-axis is how frequently they're requesting an inference from the server. And prior work has really focused on this one-time or one-off inference where there's essentially infinite downtime between two inference requests. And there they're trying to optimize for the online phase latency. But what happens as a client actually starts requesting more and more inferences? Well, first, due to the storage constraints, the two parties can only engage in a few pre-computes, and so that's one bottleneck. And the second bottleneck is that the pre-processing phase takes a long time. So at sufficiently high inference request rates, we can't mask this latency. So what we'll see is that even at one request every hour, we start to observe or pay the penalty of the pre-processing phase latency, and even at higher higher request rates, let's say one request every 30 minutes, we start to see inferences queuing up, and we're waiting for our prior request to sort of complete. And so our takeaway is that the pre-processing costs actually affect end-to-end latency when we consider multiple inferences. And so we turn to optimizing these pre-processing costs. So here's this baseline private inference protocol that we're working with, and I'll show you two of our optimizations. So the first one is that storage problem that was happening in the offline garbled circuit protocol. So let's zoom in on that. And what we'll see here is that the server performs the garbling of the ReLU, and the client actually stores these garbled circuits locally. And our insight is that either party can play the role of the garbler and the evaluator, and so we propose a novel protocol, and we call this client garbling, where we swap the roles of the two parties. And so we've moved that heavy storage cost over to the server, and we assume the server has ample storage when compared to the client device. And this allows them to engage in 5 times as many more pre-processing phases so they can buffer up those pre-computes. Now there are some caveats to doing this switch. The first one is oblivious transfer, extended oblivious transfer, moves to the online phase. Rather than downloading these garbled circuits to the client, we're now pushing them to the server. And finally, the actual computation for this protocol is swapped. Now the client is garbling, and the server is the one actually performing evaluation. So those are things to just consider. So stepping back out, here's the protocol again with our client garbler protocol. We also went and optimized the compute stack. And so again, we saw that the homomorphic evaluation took up a large chunk of that compute stack, so let's take a look at that. And so here's the actual offline protocol using homomorphic evaluation, and the expensive part comes from the evaluation of these linear layers of the neural network. And as you would suspect with the neural network, we sort of step through this, the layers sequentially and perform these evaluations. But if we look at the inputs to the homomorphic evaluation, they're actually dependent upon just random samples from both the server and the client. And so there's an independence here. And so that's the key insight we have in this part of the protocol. And we take advantage of this independence and parallelize the computation of these linear layers. And we call this layer parallel homomorphic evaluation, and it gives us a 9.7x speedup. So again, since we're using secret sharing in the online phase, we can parallelize the linear layer evaluation in the offline phase since it's input independent. And so let's see how these optimizations sort of affect the overall protocol. So here's again ResNet 18 on Tiny ImageNet. This red curve was the previous graph I showed, where the client-side storage is set to 128 gigabytes, and our proposed protocol in blue, that's set to 16 gigabytes for the client device. And we observed 2 things. First, the mean inference latency has decreased, and we've pushed out the maximal sustainable throughput, and that's because we're taking care of these pre-processing costs. But there's a catch here, which is that still the latencies we're observing are on the order of minutes, and we can still only support a request of an inference rate of 1 request every 15 minutes. And so this sort of points to the fact that we need optimizations across the stack. And so to that end, we open source and release our code called Kryptonite, where you can plug in your own optimizations, plug in your own private inference protocol, and sort of observe the system level effects on latency. And so with that, I conclude. Thank you so much, and I'm happy to take any questions.